The whole purpose of buffers is to not have their pH change. So a reasonable question is, how do you calculate the pH of a buffer? And while you can use an ice table, you can look at how the different acids and bases interact with water to create hydroniums, hydroxides, yada, yada. You can also just use what's called the Henderson-Hasselbalch equation. And so this equation comes from using a ice table description, looking at how your conjugate pair interact with water, make hydroniums and hydroxides, and you can kind of combine all of that in a single equation that's based around approximations of minimal shift using, since it's weak acids and weak bases. And you end up with this equation that the pH of a buffer is equal to pKa plus log, that's a base 10 log, and then we have the concentration of A minus over the concentration of HA. And so how we can interpret this is that the pKa, remember Ka is the dissociation constant for our acid. P means the power, or you power scale, you do negative log of the Ka. And so Ka values for the acids are usually tabulated. There's also tables with the P values. There's a table I've posted to Blackboard with the pKa values included that I encourage you to take a look at. And you're looking for the Ka of whatever molecule is the conjugate acid in the pair. Remember, a buffer is made up of a conjugate pair, acid and base. And so whatever the acid in the conjugate acid of that pair, you want that Ka. And then these concentrations over here, these are those nominal concentrations. So that's the not necessarily the concentration at equilibrium, but like the marked concentration on the solution. So, it's 0.1 molar HF or 0.2 molar, CN minus or something like that. And so whatever those concentrations are, you just plug them in. And so this becomes an algebraic problem. Basically, the ice table work, all of that kind of algebra has already been done. And this is the general expression you can always use to calculate the pH of a buffer. It does need to be a buffer in order for this solution, this equation, to be applicable. Let's take a look at an example. What is the pH of a solution that is 0.4 molar NaCN, that's sodium cyanide, and 0.4 molar HCN, that's hydrocyanic acid?
Okay, so what is the pH of a solution? And so we have calculated the pH of a lot of types of solutions, and in general, we've always had the approach of, well, pH is the negative log of the hydronium concentration. So we need to get some sort of information on the acidity of solution. And so we'd always ask ourselves, well, what's in the solution? Okay? And we can see that what's in the solution is I have NaCN and HCN. Those are my substances that are in solution. So HCN, that's a weak base. Sorry, weak acid. Hydrogen in the front. That's a weak acid. Okay, so we know it's not on our list of 6 strongs, but there's a hydrogen, so it's going to be a weak acid. Okay, very nice. So then what about NaCN? So this, if it was just HCN, this would be an ice table problem. We could figure out using the Ka what the pH is based on the concentration. And we have NaCN. Well, that's a salt. So we know it's going to be Na plus and Cn minus. And so what about those things? Well, Na plus, that's in group 1A, so that's neutral. And Cn minus is an anion, so maybe a base, and its conjugate is a weak acid. So this thing is a weak base. And so we can see we're starting to get into more complicated solutions where there's more than one thing present. And we can see explicitly that we have paired up in here, in this solution, we have a conjugate pair. The solution contains a conjugate pair. HCN is the weak acid, Cn minus is the weak base. So the conjugate pair is contained in solution, 0.4 molar, 0.4 molar. Those concentrations are very close. This thing is a buffer solution. So when we have, previously it's always been what's in solution, how does that react with water to create hydroniums or hydroxides? But now we have a complication where it's like, what's in solution? If they are a conjugate pair, it is a buffer. And if you really want, with a buffer, you can use an ice table setup and you can figure out the pH using that. But that sounds unpleasant. So what we do instead is we can say, well, I'm going to have, since it's a buffer, I can use what's called the Henderson-Hasselbalch equation. And basically, this equation comes from the fact that if you do use an ice table setup, just like we saw with weak acids, the ice table always gets solved in basically the same way. You can almost always use an approximation for a small shift because these are weak acids. And if you do that, you can get some algebra, kind of a generic algebraic expression that tells you that the pH of the solution is equal to pKa plus the log, and then we have the concentration of A minus divided by the concentration of HA. So this is the general expression of the Henderson-Hasselbalch equation. And basically what we want is the pKa is for the weak acid in the conjugate. This would be the concentration of acid. This would be the concentration of base, where the base and acid are defined for my particular buffer. So here I have this cyanide and hydrocyanic acid buffer. And so if I want to I can flesh out these variables a bit to be specific to this buffer. That pH is equal to the pKa of HCN plus the log of the concentration of cyanide divided by the concentration of HA. Oh, it's HCN, the actual acid that I'm using. So one of the things about looking up pKa's is that that is a number that's just a reference because it's the negative log of the Ka. And so you can look up the Ka on a table. So for example, HCN right here, you could look up the Ka and do the work. A lot of times, and I have a table for it, pKa values are also tabulated. So someone's already done the negative log of all these Ka values just to get the pKa. And so we can just plug that in. This would be 9.21 is the value for HCN plus the log, and then we can just plug in our concentrations that are both 0.4 molar. We get 9.21 plus the log, that's the same number divided by itself, gives you 1. The log of 1 is just 0. And so we get that the pH is 9.21. And actually this result is a general result that we're seeing, where we'll note this pH is equal to the pKa of the acid. And you will note that this is because the concentrations of your acid and base are the same. So whenever you have an acid and base concentration that are the same, that will always be 1 inside the logarithm. The logarithm of 1 is always 0. And so you get a pH equal to the pKa. So if you make a kind of perfect buffer, if you will, where the concentrations are exactly equal to each other, you expect the pH to be equal to the pKa. If the base concentration is higher, this number will be positive. So if your base concentration is higher than your acid concentration, the pH will be a little bit above the pKa. And if your acid concentration is higher, the pH will be a little bit below the pKa of that of the acid you've chosen for your buffer.
Participation 1015, question 2. What is the pH of a solution that is 1.5 molar H2CO3 and 1.3 molar NaHCO3? Second question on participation 1015 due Friday, October 15th at 11:55 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, what is the pH of a solution that's 1.5 molar H2CO3 and 1.3 molar NaHCO3? Here we go. Second question on 1015 participation is down in the books. See if there's more in the rest of our videos. See you in the next one.